Today we are going to see about the different graph traversals. Basically, if you consider any kind of tree traversals, the tree traversals can be broadly classified as three types, namely the in-order, the pre-order, and the post-order traversal. In case of in-order traversal, the root node will be present in between the left subtree and the right subtree. Similarly, in case of pre-order traversal, the root node will be present in the beginning, followed by the left subtree, followed by the right subtree. And in case of post-order traversal, the left subtree will be visited first, followed by the right subtree, followed by the root node. So, depending on the position of where exactly my root is present, the traversal will vary. Similarly, if we are going to consider the graph traversals, in case of graph traversals, there are two types, the depth first search and the breadth first search. So, depth first search, in short, it is referred to as DFS, and breadth first search, in short, it is referred to as DFS. Graph traversals can be applied to any undirected or a directed graph, provided both these graphs are unweighted. So, whatever be the type of graph which is given, whether it is undirected or directed, provided it is an unweighted graph traversal can be applied. Either it will be a depth first search or it will be a breadth first search. So, we will see it in detail what exactly these two traversals mean. So, the first traversal which we are going to see is the depth first search traversal. So, basically, the depth first search traversal makes use of stacks for its implementation. Assume like the graph which is given to me is going to have the following vertices and the following edges. We are going to apply the depth first search algorithm for this particular graph, and we are going to find out what exactly is the path which is getting visited after this particular algorithm is applied. So, assume like I am taking an undirected graph. So, we are going to make use of a stack data structure for implementing this. So, I am going to take a tabular based method for solving this above algorithm. Wherein my table it is going to have two columns. The first column represents the content of the stack, and the second column it represents the visited nodes. Here I am going to assume like B is going to be the source node. So, I am going to start the traversal from the vertex B. In case of depth first traversal, if I am going to start from a particular node, from that particular vertex, we are going to visit the corresponding descendants of that particular node repeatedly until the leaf level is reached. So, we are going to consider one single path starting from the reference node or from the root node, and I am going to come level by level until I am going to reach the last leaf level. If no more traversal is possible from the leaf level, we are going to iterate and backtrack towards parent value, and we are going to check for other possibility. So, repeatedly I am going to follow this procedure until all the vertices of the graph is completely visited. So, if my graph is a strongly connected one, in that case, a single pass of DFS will be giving me a path wherein I will be able to reach all the vertices of the graph. If it is going to be a weakly connected graph, in that case, we may require more than one pass in order to visit all the vertices of the graph. So, here we are going to see how exactly the DFS algorithm works. So, here I have assumed B is going to be the source node. So, in the visited category, directly I am going to add the vertex B, denoting that that particular vertex has been visited. So once I am uploading a value in the visited category, parallelly you are going to check for the degree of that particular vertex. So here the degree of the vertex B is going to be 2, wherein I have connections to A and F respectively. So B is connected to A and B is connected to F. So I am going to push the values in alphabetical order inside the stack. So B is connected to A and B is connected to F. And we know very well in case of a stack, whatever value was inserted first, that will not be popped out first, wherein whatever value was inserted at the end will be the first one to get popped out. So basically stacks makes use of the last in first out principle. So if I apply the principle over here, in the next iteration, I am going to retain whatever value was there in the previous iteration and I am going to pop the topmost value. The topmost value is going to be F. So once I have updated the right column, I am going to parallelly update the left column. So retain those values which is there from the previous iteration and check for any new updation. So now F is also under visited category. So now check for the degree of F. Degree of F is equal to 3 and F is having connection to B, G and E. Check whether these vertices are present either in the stacked column or in the visited column. So somewhere it should be present. If it is not present in both of these columns, we can update that inside the stack. So if we consider the first vertex B, it is already there in the visited category. So I am not going to write this again. And when you consider the remaining two values G and E, it is not present in both of these columns. So I am going to update the content of the stack in alphabetical order. So I am going to repeat this procedure again. So retain the previous value and pop the topmost value. So now currently F is popped out and currently the content of the stack is going to be A, E and G. So now the element to be popped out is going to be G. So G is going to be there in the visited column. So G is visited. Now retain the previous values and check for any new updation. G's degree is equal to 2 where G is connected to A and F. But both these vertices A and F has been updated either in the stack column or in the visited column. So I am not going to update those two values again. So what I am going to do is I am going to just continue my iteration again since there is no addition of the vertices. So this becomes B, F, G and popping the topmost value, E is the topmost value. So E gets updated. So E is also visited now. So currently the previous content of the stack is going to be A. So after adding E, check for any other new addition. E is having degree as 2. One is connected to D and the other one is connected to F. F is already there in the visited category. So the new value which I need to update it inside the stack is going to be B. So continue this iteration again. So B, F, G, E from the previous iteration and pop the topmost value. So once I have visited D, so check for any new update. Yes, D is having degree as 2. One is connected with C, the other one is connected with E. E is already updated in the visited category. So the only new value which I need to update is going to be C. So retain the previous value and update the new value. So continue this procedure. B, F, G, E, P and I have a C. So now after adding the vertex C, check for any new updation. So C is having degree as 2. C is connected to A and C is connected to D. A is present inside the stack and D is present inside the visited column. So anyways, within these two columns, I have both these vertices, which means that there is no new addition of vertex. So continue with popping operation. So A, E, F, G, E, C and A and the content of my stack is going to be different. So this is going to be the end of this iteration and this is the final DFS traversal for this particular graph. So if we consider the path, so from B it is going to F and from F it is going to G and from G it is going to So in this particular path, we have connection from B, F and G. So again, I am going to backtrack and I am going to check for any other possibility. So B, F, E is the next path. From E it is going to D, from D it is going to C, and from C it is going to A. So this is going to be the end of the iteration. So here in this particular BFS traversal, you are going to have two paths wherein B is going to act as the root node. The first path is going to have B, F and G. So after this I don't have any more traversals, so I'm going to backtrack and move on to the previous value. So from F I have another one path, so which is E, B, C and A. So this is going to be the final depth first traversal for this particular graph. So now we will see how exactly a breadth first traversal can be applied. A breadth first traversal is more or less similar to level order traversing, wherein all the values which is present in a particular level will be given with equal priority. So in with reference to the previous thing, our BFS is basically makes use of queues for its implementation, which is in turn nothing but first in first out logic. So we'll consider a graph for which we are going to apply the BFS traversal. So assume like this is the graph which I have considered. So for this particular graph, I am going to apply the BFS traversal. So here again, I am going to follow a tabular approach for solving the problem, wherein I am going to have two columns, namely the queues and the visitor nodes. So here again I am going to assume B is going to be the source node. So B is going to be directly present inside the directly placed inside the visitor category. So check for the degree of B similar to BFS traversal. So the degree of B is equal to 3. So B is connected to A, B is connected to D and B is connected to E. So similar to the previous problem, here again we are going to update the content of the queues in alphabetical order. But the only difference between BFS and the BFS traversal is that in case of stack based traversal, we are going to pop the topmost element. Whereas in case of this queue based traversal, we are going to delete the first element which was inserted, since this is before logic. So inside the queue, the content of the queue is going to be A, D and E. So since this is queue, the first element to be dequeued is going to be A. So BA is the one which gets updated first. So now B is also updated and A is also updated. Retain the previous values. So once you have retained the previous value, check for any new update. A is having degree as 3. A is connected to B, A is connected to C and A is connected to D. Out of these three values, B is present in the visited category, D is present in the queue. The only new value which I need to update is going to be C. So C gets updated. So retain the previous value and dequeue the first value. So inside the queue, D is the first value, so D gets dequeued. So retain the previous value and check for any new updates. B's degree is equal to 3. D is connected to A, D is connected to B and D is connected to F. A is already present inside the table. B is also present inside the table. So F is the one which gets newly updated. So F gets updated here. So continue this operation again until my queue is completely empty. So the next element to be dequeued is going to be E. So remaining values you are going to retain as C and F. So now you check for any new vertices. So B, A, D is visited, E is also visited. So after updating the value E, check for the degree of E. E is connected to B as well as E is connected to G. Wherein B is already present in the table, the only new value which I need to update is going to be G. So G gets updated. So B, A, D, E from the previous iteration and DQ the first value. So the first value is C. Check for any new updates. even though G is connected to E and F, both E and F is present inside my table already. Since I don't have any addition of the values, I'm going to continue with the iteration again, wherein I'm going to DQ the first element. The first element is going to be F. So now also I'm not going to have any new addition. So I'm going to continue this operation again. So delete the only element. So this is going to be the end of iteration. So if you look into the corresponding representation, minimum spanning tree and spanning tree representation of this particular graph, B is going to be the root node, B is connected to A, B is connected to E, and B is connected to E. So B is in the first level, A, D and E are in the second level. Next, we are going to have the vertex C. In the C, the connection is through A. So from A, I have a connection to C, and from C, I have a connection to D, I have a connection to F, and from D, I have a connection to G. This is a equivalent spanning tree representation of the above result. So there is no need to represent this in terms of a spanning tree, wherein this last step is more than enough to say whether it is possible to visit all the vertices of the graph or not.